So, pretty excited to be here today. Pretty excited to talk to you about this research. I enjoyed to do it, and I hope that you will enjoy hearing about it. Before we start with the research, let me introduce myself. So I'm Vera Mens, a vulnerability researcher at Clarity, Team 82. Team 82 is a vulnerability research team that focuses mostly on IoT and OT devices, starting from embedded end devices and up to OT and IoT cloud infrastructures. As for me, I mostly enjoy doing the embedded stuff, so that's what I'm mostly focusing on. Also, occasionally, we do participate in Pwn-to-Own competitions, which is quite cool, and actually got a Master of Pwn award from the last Pwn-to-Own Miami. Yeah. So being here today at this stage is pretty special for me, and I would like to share with you why. This picture behind me was taken 7 years ago on the first BlueHat night event back into 2017. I was a curious software engineer going to security meetups just to know about and learn about new stuff. As for me, to be a vulnerability researcher, I was convinced that being a vulnerability researcher, you have to be a young special units alumni and not some almost 30 years old developer. I was convinced that being in the audience of the conferences, this will be the highest that I will ever go. And being here today proved me wrong, and I'm really proud of it. And the reason I'm telling you about this is because in case there is someone in the audience today that thinks that the door's closed to him because he doesn't answer to that specific profile, you should know that it is possible, and you just need to really, really want it, and it can happen. So enough with the TED Talk, okay? We finished with that. Let's start with hacking. Yeah, so the background for this research, as it starts with many research in our team, my team lead, Sharon, comes to me saying that the customer requests a detection mechanism for one of the proprietary protocols of one of the equipment the customer had in its lab. It's called Gas Chromatography, something like that, what? And it's not that strange. At Clarity, we do perform protocol research all the time. But the main caveat here is that apparently gas chromatograph are devices that are not that easy to find and acquire. And we had to do this job without it. And before we proceed to the detection phase, let me just tell you a couple of words about the gas chromatography. Not because it's somehow related to the research, it's not. It's just super cool, and I would like to share it with you. So the gas chromatography is a technique used in the chemical industry to take a mixture, a liquid mixture, and to separate it into different compounds. And it utilizes two chemical characteristics. The first one is that each element have a different and distinct vapor point. And the second one is that each element will travel in the gas phase much faster than in the liquid. No pun intended here. So what we know from here, and the main general techniques that used here, is that we can inject the liquid here to the main column and start to heat it up. The liquid will heat and will evaporate, and each element in each distinct time will hit the detector. The detector will record all the points it detects some element, and later on it can be compared with previously known evaporation times. And that's how each element could be detected within the mixture. So I'm not sure that I told it right, and I'm not a chemist, but for me it was pretty cool, and I want to talk to you about it. So how do we start to develop a detection methodology for the protocol we know nothing about, and for the device we have nothing useful about it. And of course, it's by reading the documentation. And there is a lot of it in the official website. Nothing that's useful for me as a researcher too much, but we do know some things. The first of all is that how our device looks like. And we actually can see, I'm too short, but let's go and see above. We actually can see the column and the place where the gas can be injected. And what is interesting for us as vulnerability researchers will be what the protocols this device supports and how the device can be communicated remotely. So it appears to be that there is a Windows software the technician would install on its Windows machine, and the technician would be able to communicate with the device remotely from its computer. So in high level, that's how it looks like. We have our technician that runs the client, the software client that used for data acquisition, monitoring, and configuration. We have those devices that sit in the laboratories, and we have some protocols that, of course, it's not documented, but we do know that it used above TCP 10,000 and is encrypted with TLS protocol. That's all we know. So how do we start a proprietary protocol analysis, and what is our end goal? Our end goal is to develop a detection mechanism that will be able to view into the payload, data payload of the protocol, and to identify this is the protocol, this is what it is. There is no official name for it. Let's call it protocol 10,000, okay? And as for me, the researcher, what I need to do and what I need to have in order to do this job properly is to have the closest setup to the real one as I can have, which means I need the Windows client, which fortunately for me can be downloaded from the official website. I would like to have the device, which I don't. This one we already know. And of course, I would like to be able to view and hopefully alter the communication, so I would be able to correctly classify it and understand its structure. So, as I said, we do have the Windows client, so let's start with it. We can already start to understand the protocol. Even though we don't have the running setup, we do have one part of it, and we can start going around the UI and start to explore the configuration available and maybe some of the functionalities. Also, we can plug the code into IDA and start to research the code itself. It's not that easy because we need to find the implementation, and the protocol implementation can be quite complex. But the question arises, can we do our job, our task, which is develop a detection mechanism statically, only by reviewing the code of the Windows client? And the answer is, of course, yes, because the protocol is supported by the client. The client have to know how to construct each of the payloads. So by research every code base of the client, we should be able to reconstruct it. But practically, it will take ages. And as for me, I was back then on 6-month pregnancy with my baby girl, and my timeline was pretty strict. So I had no time to do this. I needed to proceed with the other side of the setup, and hopefully to emulate the world communication. Sorry. So where we are at now, we have our Windows client up and running. we use the IDA for basic understanding, and now we need to get somehow the device. But we don't have the device, okay? We don't have it. And the other option for us would be emulated. And why we don't have it, you would ask, is my boss is a cheapskate, that's why. That's the other reason. So that's why I don't have it. And I had to somehow to do without it. And when we come to device emulation, there are two main questions that we need to answer. And the first one is what? We do not need any gas chromatography to do in our place. We do not looking for vulnerabilities in chemistry. The only thing that we care about is implementation of the protocol. And the implementation of the protocol is just compiled into some binaries that sits on the firmware that runs on the actual board. So by acquiring the firmware, we should be OK to go. And fortunately for me, the firmware was available online, so we just download the file and extract it. So cool, the gas chromatographs runs on Linux, not that special, right? Mars rovers runs Linux as well. So, so this is pretty cool because it's something that we are very familiar with, and we can start with find the main application, right? Our goal here right now, we have the firmware, but we still don't know where sending the applications and implement the protocol. We need to remember, though, that this is not a general-purpose computer. The application that runs and the protocol, the implementation of it, should be started right after the boot time. So by going from the init tab process up and reviewing all the initiation files, we should find it somehow. What we are looking for is some binary that will call a bind function to the port 10,000. That's it. That's all we need to find. And the time it will take to find this binary depends both on luck and the experience, but sooner or later it will happen. And the question is coming here as well. Can we do static analysis here, reversing the binary of the device side is quite easier because we don't have the UI overhead, but it's still a lot of work, so we need to proceed with the emulation. The second, okay, yeah, theoretically, yes. The second question we need to answer about the emulation is how. How do we do it? And our Gas Chromatograph runs on PowerPC CPU, and for PowerPC, the way to go for the emulation is QEMU. So we have a QEMU for a PowerPC, which emulates quite a range of machines. I chose the one from Macintosh that used by Apple before they switched the architecture for the first time. And I needed an operating system, and I needed a bootloader, of course, because what I have from the official website is only the firmware. So Ubuntu PowerPC was the easiest choice. Ubuntu is compiled for everything, And after some hours of figuring out those command lines, which takes a lot of time. It looks easy, but it's not. We need just to remember port forwarding the ports for our application and SSH for the convenience. And we have our PowerPC Ubuntu up and running on QEMU PPC. The next thing for us to do is to take the firmware that we have downloaded from the website, copying it to the Ubuntu operating system, and using chroot command to make the firmware file system our own root. So this setup is quite confusing, so let's just summarize it. We have our Gas Chromatograph file system that is rooted from the Ubuntu PowerPC that runs that Ubuntu PowerPC runs on QEMU. QEMU is installed on Ubuntu from my virtual machine that runs on Intel architecture, which in turn is a VirtualBox installed on my Mac. You can use QEMU directly from Mac. There is no problem with that. You just need to be more arrangements, and I didn't want to go through that. So we are ready to run our main application. We do have the executable. We have our running environment, and we just need to do some preparation. We looked through the init files, and the execute only must-have stuff like defining the environment variables, creating the directories, just some try and fail thing, and this is where we are ready to run our executable, and it won't run for long. Okay, our Macintosh machine doesn't have the peripherals that the Gas Chromatograph have, and we somehow need to deal with that. But we need to remember that our goal here is not to run gas chromatography, and only to inspect the protocol. So what we need to do is to patch every call of the system that calls those peripherals, and we will be good to go. So right now we have some dance with run crash patch. Run crash patch dance, but eventually, sooner or later, we will come to this. So we will be able to use our client software and connect with it to our emulated device and see the communication. Whew, the hardest part is over, isn't it? And we can maybe start to analyzing the protocol. Not yet. Another thing that we need to cope with is the encryption. As we saw in the documentation, the protocol is encrypted with the TLS. So fortunately for me, the device supports plain text communication. And what I need to do was what I had to do is just find a client that is old enough that he doesn't support the encryption, so I would be able to communicate in plain text. Of course, I didn't do that. Just another patch to lie about my version, saying that my version of the client is too old and I do not support the encryption, so now everything works as expected. So now we have a couple of days doing this, reverse engineering the client, the server, and analyzing the communication in Wireshark. So after some time, we will come to this rather simple protocol, 16 bytes at header, and the data payload accompanied after. The payload depends on the CMD types, and the protocol supports several CMD types. The only one that was short enough to be fit in this presentation is the change level. So let's look at this one. This is a very simple one. The only thing that we see here is the name and something that's called level. It's this administrative level that a user would like to change to. And that's it, a very simple command. We need to do it for each command type that the device supports, document it, and develop a detection for it. So that's cool. We can finish this one and proceed to the next project, but not yet. Let's take advantage of the setup that I worked so hard for and find some vulnerabilities. So let's see if the protocol is secure. Let's find out. We have a pretty good setup here. We have our client, we have the emulated device, and our setup resembles pretty much the real one, apart from the encryption, which is not something that we worry about. And we can start to answer the question about the security. And this is a fast answer. This is a short answer for it. So we have pre-authenticated remote code execution, and before we will look into this vulnerability, let me show what I did to find it. So usually what I do in this type of the research, I go for every command type and look for logical vulnerabilities like command injection, path traversal, SQL injection, and so on. And also for memory corruptions, which are much harder to exploit. So the logical ones are much more preferable if they exist. So this is a problematic command that I have found. It's called forced calibration. And from the manuals, we can see that forced calibration command uses an archive chromatograms to calibrate the device. So let's see how those archives are used. So some of you already see the problem here. We have here a shell command constructed from the input from the user, and then the command is provided to the system function, which then will be evaluated with a shell. And this is pretty straightforward command injection vulnerability. For command injection vulnerability to be successful, we need two conditions to meet. The one is that the input for the command is something that I can control. And the second one is the sanitization is poor or does not exist. For me, both of them met, and I could provide, instead of the files that I want to expand in the gunzip, I could provide a reverse shell command and triggers the vulnerability, and this is what I get from it. Okay, so we have pre-authenticated, no authentication needed to use this vulnerability, and maybe there is something else. And vulnerabilities that I would like to mention is a cute one, because you could spot it only by reading the documentation without going through the code, without any reverse engineering whatsoever. Look at this one. This is procedure to reset the administrator password. There is two stuff that we need to note. The first one is that administrator password can be reset without the factory reset by supplying the passphrase. This is very bad security practice, right? You wouldn't want to have your phone PIN code being able to be reset without if you forget your password, right? And the second one is that administrator username is known in advance and cannot be changed. It says here that if the username is deleted, it is created again. So here we know that we have some an authentication bypass vulnerability. We still do not know what the passphrase is needed to enter the system, but we do know that this one this is something that we can get. So what do we know? We know the username, and we know that there is some passphrase that will reset the administrator passphrase that will reset the administrator password. And the next thing for us to do will be to see how this passphrase is validated. So let's look at the code. We have some challenge key. We don't know. We still don't know what it is, but we get that key, and we do some shifts and additions to get some hash digest, and then this digest is compared with the user input. That's it. It looks like that if I will get the challenge key, I will be able to enter the system, right? So this is how the challenge key is calculated. For those who cannot see the slide, this is the MAC address of the system. That's it. By knowing the MAC address of the device, I can calculate the passphrase, do the reverse algorithm of the one used here, and be able to connect to the device. And this is how it looks like. OK, that's cool. We did successfully enter the system, and we all happy that we can move to the next project of our own. And from here will be the disclosure process. The disclosure process starts with Emerson. We reported them the vulnerabilities. They worked with us to fix them, and they fixed them pretty promptly. And CISA published an advisory that publishes all the 4 of the vulnerabilities we have found. And that's it for this talk. Be sure to check our blog. And if you have any question, you can reach me and ask questions. I would like to answer them. Thank you.